On October 9th, 2022, something happened that should not have been possible. A wall of energy, older than any animal that has ever lived on Earth, crossed 2.4 billion light-years of empty space and struck our planet. It had been traveling since before multicellular life existed. It arrived in silence, invisible to the naked eye, and yet it was the single most powerful burst of electromagnetic radiation ever recorded in the history of modern astronomy. Every gamma-ray detector in orbit was overwhelmed. Several instruments saturated completely, their sensors unable to measure what they were receiving, because the signal was simply too strong. The numbers, when scientists finally reconstructed them, were so extreme that some researchers initially assumed their equipment had malfunctioned. This was not a supernova. It was not a collision of galaxies or the death spiral of two black holes. It was something rarer, something the universe produces, perhaps once every 10,000 years within our observable horizon. It was a gamma-ray burst, and not just any gamma-ray burst. It was the most luminous event recorded since the invention of instruments capable of detecting such things. Astronomers gave it the designation GRB 221009A. But among themselves, in laboratories and observatories around the world, they called it something else. They called it the But, the brightest of all time. The energy released in this single event, concentrated into a narrow beam of radiation, exceeded the total light output of every star in the Milky Way combined. Multiplied by a factor of thousands, compressed into a flash that lasted only a few hundred seconds at its peak. That energy tore through intergalactic space, crossed a distance so vast that light itself needed 2.4 billion years to make the journey, and still arrived with enough force to measurably disturb the upper atmosphere of Earth. A burst from across the cosmos altered the ionosphere of our planet, the layer of charged particles that surrounds Earth, the same layer that makes long-distance radio communication possible, rippled like a pond struck by a stone, except the stone had been thrown from the other side of the universe. We are accustomed to thinking of cosmic events as distant, abstract, irrelevant to daily life. Stars explode, black holes swallow matter, galaxies collide, and none of it touches us. We go to work, eat dinner, check our phones, sleep, and wake to a world that seems unchanged by the violence unfolding in the depths of space. But on that autumn day, the universe reached across an almost incomprehensible distance and physically altered the atmosphere above our heads. Not enough to harm anyone, not enough for any human to feel, but enough for instruments to detect, enough to prove, with hard data, that we are not as insulated from the cosmos as we like to believe. By the end of tonight, you're going to understand what GRB 221009A actually was, why the universe produced it, why nothing in recorded history compares to it, and what it tells us about the violent, unstable nature of the cosmos we inhabit. You are going to understand why astronomers around the world stopped what they were doing on that October day, and why the data from this single event will take decades to fully unravel. More than that, you are going to understand what it means to live in a universe where events of this magnitude are not anomalies but inevitabilities, separated only by spans of time too vast for human intuition to grasp. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. This is a story about the most violent thing the universe has done in our lifetime. It is a story about distance, about energy, about the death of massive stars, and about the thin, fragile membrane of safety that separates us from a cosmos that does not care whether we exist. It is also a story about what happens when nature exceeds every prediction, every model, every expectation that science has carefully built over decades of observation. Because on that autumn day in 2022, the universe reminded us that our understanding has limits. And those limits are not comfortable. They are not reassuring. They are, if we are honest with ourselves, quietly terrifying. The photons that triggered the alarms were born in the death of a star, not a gentle death, not a slow fading. A catastrophic implosion, a collapse so violent that it punched a hole in the fabric of spacetime and created a new black hole. From the poles of that dying star, two jets of matter erupted at 99.99% the speed of light, carrying energy so concentrated that nothing in our solar system, nothing in our galaxy, produces anything comparable. Those jets crossed the gulf between galaxies. They crossed the void between galaxy clusters. They traveled for longer than complex life has existed on Earth. And one of them, aimed with the precision of a cosmic sniper, happened to be pointed directly at an unremarkable planet orbiting an unremarkable star in the outer arm of an unremarkable galaxy. That planet was ours. That beam found us. Now let's begin. To understand what happened on October 9th, 2022, we first need to understand what a gamma-ray burst actually is and why the universe produces them. Because nothing about this phenomenon is intuitive. Nothing about it fits neatly into the categories that everyday experience teaches us. A gamma-ray burst is not like a lightning strike or an explosion or a fire. It is something else entirely. Something that belongs to a scale of violence that the human mind was never designed to process. Gamma rays are the most energetic form of light. They sit at the extreme end of the electromagnetic spectrum, beyond visible light, beyond ultraviolet, beyond even X-rays. A single gamma-ray photon carries millions or even billions of times more energy than a single photon of visible light. On Earth, gamma rays are produced in nuclear reactors, in particle accelerators, and in the detonation of nuclear weapons. They are the radiation that penetrates lead shielding, that damages DNA, that makes certain kinds of nuclear waste lethal for thousands of years. They are, by any reasonable definition, the most dangerous form of light that exists. Now imagine a source of gamma rays not in a laboratory, not in a reactor, but in the depths of space. Imagine a source so powerful that it outshines entire galaxies. Imagine it turning on without warning, blazing for a few seconds or a few minutes, and then vanishing forever as though it never existed. That is a gamma ray burst, and the universe produces them with disturbing regularity. The story of their discovery begins not with astronomers, but with spies. In 1967, the United States military launched a series of satellites called Vela. Their purpose was not scientific, it was political. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear weapons tests in the atmosphere, in outer space, and underwater. The Vela satellites were designed to detect the gamma-ray signatures of clandestine nuclear detonations to catch any nation that might try to test a bomb in secret. They were instruments of surveillance, orbiting sentinels watching for the telltale flash of a prohibited explosion. What the satellites found was something no one expected. They detected brief, intense flashes of gamma rays coming not from Earth, not from the Soviet Union, not from any terrestrial source at all, but from deep space. The flashes appeared at random, from random directions, with no obvious pattern. The military analysts who first noticed these signals were baffled. The detections did not match the signature of any nuclear device. They did not come from the ground or the atmosphere. They came from everywhere, from all directions, from somewhere far beyond the planet. The data was classified for years. It was not until 1973 that the results were declassified and published by Ray Klebsdell, Ian Strong, and Roy Olson of the Los Alamos National Laboratory. Their paper, modest in tone, announced the detection of 16 gamma-ray bursts of cosmic origin between 1969 and 1972. The astronomical community did not know what to make of it. There was no known mechanism that could produce gamma rays at such intensities from beyond the solar system. For the next 2 decades, gamma-ray bursts remained one of the deepest mysteries in astrophysics. More than 100 different theoretical explanations were proposed. None were conclusive. To appreciate the scale of what these events represent, consider the following comparison. Our Sun is a fairly ordinary star. It converts roughly 4 million tons of matter into energy every single second through nuclear fusion in its core. 4 million tons every second for billions of years. This has been happening for about 4.6 billion years, and it will continue for another 5 billion years or so. The total energy output of the Sun over its entire 10 billion year lifetime is a number almost beyond comprehension, roughly 3.8 times 10 to the 53 ergs. It is the kind of number that has no analogue in human experience, yet a single gamma-ray burst can release more energy in 10 seconds than the Sun will produce in its entire existence. Not twice as much, not 10 times as much, hundreds of times as much, concentrated into a beam that lances across the universe at the speed of light. Here is a scaled comparison to help anchor this. Imagine that the total energy output of our sun over its entire lifetime could be represented by a single grain of sand. That grain of sand contains all the warmth, all the light, all the energy that the sun has ever given, or ever will give to the solar system over 10 billion years. On that scale, the energy released by a powerful gamma-ray burst would be a boulder the size of a house. That is the difference we are talking about. A grain of sand versus a boulder. One is something you brush off your hand without thinking. The other could crush a building. That is the gap between the lifetime energy of a stable star and the momentary fury of a gamma-ray burst. For years, the central question was simple. Where were these bursts coming from? Were they happening inside our galaxy, relatively close by, produced by some exotic but local phenomenon? Or were they cosmological, originating in distant galaxies billions of light years away, which would make them almost unimaginably powerful? The answer came slowly, through decades of patient observation. The satellite that proved most crucial was NASA's Compton Gamma Ray Observatory, launched in 1991 aboard the Space Shuttle Atlantis. It carried an instrument called BAT, the Burst and Transient Source Experiment, which was designed specifically to detect and locate gamma-ray bursts. Over its 9-year mission, BATS detected over 2,700 bursts, and it established a key fact that changed everything. The bursts came from all directions equally. They were distributed uniformly across the sky, with no concentration toward the plane of our galaxy or toward the galactic center. This isotropy, this evenness, was a powerful clue. If the bursts were happening in our galaxy, they would cluster along the galactic plane, just as stars and nebulae do. The fact that they did not meant they were coming from much farther away. They were cosmological. They were happening in galaxies scattered across the observable universe. Then came the breakthrough. The Italian-Dutch satellite BepISAX, launched in 1996, had the ability to rapidly determine the position of a burst with enough precision that ground-based telescopes could follow up. On February 28, 1997, BepISAX detected a gamma-ray burst designated GRB 970228. Within hours, optical telescopes had been aimed at the location. They found a fading point of light, the afterglow of the burst, and behind it, a distant galaxy. The distance was measured using redshift, roughly 6 billion light-years. The mystery was solved. Gamma-ray bursts were not local, they were extragalactic, and they were putting out energy at a rate that staggered the imagination. In the years that followed, a fleet of space-based observatories transformed our understanding. NASA's SWIFT satellite, launched in November of 2004, was designed specifically to respond to gamma-ray bursts. When its burst alert telescope detected a flash, the entire spacecraft would rotate, or slew, to point its X-ray and optical telescopes at the source within 60 to 90 seconds. This rapid response allowed astronomers to catch the earliest moments of the afterglow, the critical first minutes when the fading radiation carries the most information about the explosion. The Fermi Gamma Ray Space Telescope followed in June of 2008. Named after the Italian-American physicist Enrico Fermi, it carried two main instruments. The Large Area Telescope observed the gamma-ray sky with unprecedented sensitivity and energy range, detecting photons with energies up to hundreds of billions of electron volts. The gamma-ray burst monitor watched the entire sky not blocked by Earth, covering a broad range of energies and detecting roughly 240 bursts per year. Together, SWIFT and Fermi created a comprehensive real-time monitoring system. They could detect a burst, locate it, observe its afterglow, and relay the position to ground-based telescopes, all within minutes. These instruments revealed that gamma-ray bursts fall into two broad categories. Short bursts last less than about 2 seconds. They are now understood to result from the merger of two compact objects, typically two neutron stars, or a neutron star and a black hole, spiraling inward over millions of years until they catastrophically combine. The gravitational wave event detected in August of 2017, GW170817, confirmed this picture. It was a neutron star merger accompanied by a short gamma-ray burst. Long bursts last more than 2 seconds, sometimes for minutes or even tens of minutes. These come from a different source entirely. They are produced by the death of extremely massive stars, stars with initial masses exceeding roughly 25 solar masses, that collapse under their own gravity to form black holes. Here is a second comparison to carry with you. Imagine shrinking the entire Milky Way galaxy down to the size of a dinner plate, roughly 25 centimeters across. On this scale, the Sun would be an object far too small to see with any microscope ever built. The nearest star to the Sun, Proxima Centauri, would be about a hair's width away, and the distance to the host galaxy of GRB 221009A, 2.4 billion light-years, would be approximately 570 meters. That is more than 5 football fields laid end to end. The burst happened in a galaxy so far from our dinner plate Milky Way that you would need to walk several minutes to reach it, and yet the flash of energy from that distant point was powerful enough to be detected by instruments on our tiny, invisible speck of a sun. When a massive star runs out of nuclear fuel, the sequence of events that follows is both rapid and violent. The star has spent millions of years fusing lighter elements into heavier ones, building up an onion-like structure of layers: hydrogen on the outside, then helium, carbon, neon, oxygen, silicon, and finally an iron core at the center. Iron is the end of the line. Fusing iron does not release energy, it absorbs it. When the iron core grows beyond a critical mass of roughly 1.4 solar masses, known as the Chandrasekhar limit, it can no longer support itself. In less than a second, the core collapses. The collapse is not gentle. The core implodes at roughly a quarter of the speed of light, compressing matter to densities greater than 100 trillion grams per cubic centimeter. At these densities, protons and electrons are crushed together to form neutrons, releasing a flood of neutrinos. If the original star was massive enough, the core does not stabilize as a neutron star. It continues collapsing, forming a black hole. The surrounding material, the outer layers of the star, begins to fall inward as well. But not all of it falls in. Some of it spirals, forming a rapidly rotating disk of superheated matter around the newborn black hole. This is the accretion disk, and it is the engine that powers the gamma-ray burst. Magnetic fields, twisted and amplified by the violent rotation of the disk, channel some of the infalling matter into 2 narrow jets that erupt from the poles. These jets punch through the outer layers of the dying star and rocket outward at velocities approaching the speed of light. The material in the jets moves at Lorentz factors of hundreds, meaning it is traveling at 99.99% or more of light speed. At these velocities, the physics becomes extreme. Time dilation, length contraction, and relativistic beaming all play critical roles. The gamma rays are produced within these jets by internal shocks where faster material catches up to slower material and collides, or by magnetic reconnection events, or by the interaction of the jet with the surrounding stellar material. The focusing of this energy is critical. Because the jets are narrow, typically spanning only a few degrees of arc, the energy is concentrated into a small solid angle rather than being spread over the entire sky. If Earth happens to lie within that narrow cone, even at a distance of billions of light years, the burst appears extraordinarily bright. If we are outside the cone, we see nothing, or at most a much fainter afterglow. This means that for every gamma-ray burst we detect, there are many more that we miss because their jets are pointed elsewhere. Here is a third-scaled comparison, one that brings the speed of these jets into focus. Light travels at approximately 299,792 kilometers per second. At this speed, light can circle the Earth 7.5 times in a single second. It reaches the Moon in about 1.3 seconds. It reaches the Sun in about 8 minutes. The material in a gamma-ray burst jet travels at 99.99% of this speed. If you were somehow standing beside the jet, you would not see it pass. It would be there and gone faster than any nerve in your body could transmit a signal. At highway speed, roughly 100 kilometers per hour, crossing the distance from the Earth to the Sun would take about 170 years. Light does it in 8 minutes. The gamma-ray burst jet does it in just barely more than 8 minutes. The difference between the speed of the jet and the speed of light is so small that it would take extraordinary instruments to measure it, and yet even that tiny difference has important consequences for the physics of the burst. By the time the Fermi telescope launched in 2008, the basic picture was well established. Gamma-ray bursts were the most energetic events in the universe after the Big Bang itself. They occurred roughly once per day somewhere in the observable universe. They came in two types, short and long, with different origins but comparable violence. They were detected across a vast range of distances, from relatively nearby galaxies to the edge of the observable universe. Most were powerful, but within the range that standard models could explain. They were extraordinary, but they were understood, at least in broad outline. But there is more to this foundation than the physics of jets and collapsing stars. To understand why GRB 221009A mattered so much, we need to appreciate the sheer improbability of detecting it at all, and the chain of technological development that made the detection possible. Because the story of gamma-ray bursts is also a story of human ingenuity, of instruments built to answer one question that ended up answering an entirely different one, of decades of incremental progress that culminated in a single extraordinary observation. Consider the chain of events. Military satellites designed to monitor nuclear weapons tests discovered a cosmic phenomenon. That discovery led to dedicated scientific missions. Those missions led to new theories. Those theories led to better instruments. Those better instruments led to more detections. And more detections, accumulated over decades, built a statistical framework that allowed scientists to recognize immediately and unambiguously when something extraordinary happened. Without the Vela satellites, there would have been no Compton Observatory. Without Compton, there would have been no BEPASAX. Without BEPASAX, there would have been no Swift. Without Swift, there would have been no Fermi. And without Fermi, we might never have known that on October 9th, 2022, the universe produced the most luminous burst in recorded history. Each step built on the one before. Each instrument answered old questions and raised new ones. The entire edifice of gamma-ray burst science, spanning more than half a century, was necessary for us to recognize the significance of what happened that day. Here is another way to grasp the energy involved. Imagine taking every nuclear weapon ever built by every nation on Earth, roughly 13,000 warheads at current count, each with a yield averaging perhaps 300 kilotons of TNT equivalent. Detonate them all simultaneously. The total energy release would be roughly 1.6 times 10 to the 25 ergs. That is the combined nuclear arsenal of the entire human species, every bomb, every warhead, every device, all at once. Now consider that a typical gamma-ray burst releases approximately 10 to the 51 ergs. The ratio between the burst and the entire nuclear arsenal is approximately 10 to the 26, or 100 trillion. The burst releases in seconds what the combined nuclear weapons of humanity could produce if detonated 10 trillion times over. Numbers like these resist comprehension. They are too large for the brain to process in any intuitive way. So let us try one more comparison. Imagine that you could collect all the energy that falls on the entire surface of the Earth from the Sun in 1 year. The Sun delivers roughly 5.5 times 10 to the 31 ergs to the Earth annually. This is the energy that drives the weather, powers photosynthesis, warms the oceans, and sustains all life on the planet. A gamma-ray burst releases in a few seconds the equivalent of the Sun's delivery to Earth over roughly 20 billion years, or twice the current age of the Sun. The entire energy infrastructure of our planet, the sunlight that sustains every living thing, is a rounding error compared to a gamma-ray burst. These numbers are not abstractions. They are the measured reality of the universe we inhabit. They were calculated from real data, gathered by real instruments, analyzed by real scientists. They are as concrete and verifiable as the temperature outside your window or the distance to the nearest grocery store. The difference is only one of scale. There is another aspect of gamma-ray bursts that deserves attention before we move to the specific events of October 2022, and that is the concept of the afterglow. The initial flash of a gamma-ray burst, the prompt emission, lasts from milliseconds to hundreds of seconds, but the story does not end there. As the relativistic jet plows into the surrounding medium, the gas and dust floating in interstellar space, it creates a blast wave, a shock front that expands outward, sweeping up and heating the ambient material. This blast wave generates radiation at lower energies than the prompt gamma rays. X-rays at first, then ultraviolet, visible light, infrared, and eventually radio waves. This fading, multi-wavelength emission is the afterglow, and it can persist for days, weeks, months, and in some cases years. The afterglow is crucial because it carries information that the prompt emission does not. The prompt gamma rays tell us about the jet's internal physics, the collisions and magnetic processes within the jet itself. The afterglow tells us about the jet's interaction with its environment, the density of the surrounding medium, the total energy of the blast wave, the geometry of the jet, and the microphysics of particle acceleration at the shock front. By monitoring the afterglow across multiple wavelengths and over extended periods, astronomers can reconstruct a detailed picture of the explosion and its aftermath. For most gamma-ray bursts, the afterglow fades below detectability within weeks. The host galaxy, typically a faint smudge visible only through large telescopes, is all that remains. But for a burst as nearby and powerful as GRB 221009A, the afterglow was extraordinary. It was bright enough to track for months across the entire electromagnetic spectrum, from radio frequencies, measured by arrays of giant dish antennas, to X-rays captured by orbiting telescopes, providing an unprecedented dataset for testing theories of gamma-ray burst physics. It was this afterglow, as much as the initial flash, that would reveal the deepest puzzles about the event. Because when scientists began to analyze the fading light in detail, they'd discovered that the standard models, the well-tested frameworks that had successfully explained hundreds of previous bursts, could not fully account for what they were seeing. The data was richer, stranger, and more challenging than anything in the existing catalogue. And that is what makes this event different from the thousands that came before it. Not merely its brightness, though that was record-setting. Not merely its proximity, though that was fortunate, but the quality and quantity of the data it produced. For the first time, scientists had a gamma-ray burst so bright and so close that they could measure details that were normally lost in the noise, details that exposed the limits of theories built on dimmer, more distant events. And then came October 9th, 2022, and everything that was understood was suddenly not quite enough. At 13 hours and 17 minutes Universal Time on October 9th, 2022, an alert triggered simultaneously on multiple spacecraft. The Fermi gamma-ray burst monitor registered an incoming signal so intense that its detectors saturated within moments. Saturation means the sensors were receiving photons faster than they could count them, like trying to measure a waterfall with a teacup. The data that should have appeared as a smooth curve, showing the rise and fall of brightness, instead showed a flat line at the instrument's maximum reading, a ceiling beyond which no measurement was possible. The burst had exceeded the design limits of one of the most capable gamma-ray observatories ever built. At the same time, the Neil Gehrels Swift Observatory detected the event. Swift's Burst Alert Telescope provided an initial position on the sky within seconds. The spacecraft autonomously slewed its X-ray telescope, an ultraviolet, and optical telescope to observe the emerging afterglow. Data poured in from every direction. The European Space Agency's integral satellite, orbiting Earth in a highly elliptical path, confirmed the detection independently. The WIND spacecraft, positioned near the first Lagrange point between Earth and the Sun, roughly 1.5 million kilometers from Earth, registered the burst. The KLET instrument aboard the International Space Station recorded it. The Solar Orbiter spacecraft, designed to study the Sun, captured data from its unexpected guest. Even the Mars Odyssey spacecraft, orbiting the red planet, detected the burst from its position on the other side of the inner solar system. On the ground, automated alert systems relayed the position to observatories worldwide. Within minutes, telescopes on multiple continents swung toward the constellation Sagitta, the Arrow, a small constellation in the northern sky where the burst had appeared. Optical telescopes detected a rapidly brightening point of light. Radio telescopes prepared for follow-up observations. The global astronomical community, shifted into a mode of coordinated urgency that few events trigger. Within hours, the astronomical world was electrified. The initial brightness estimates, even accounting for the saturated instruments, placed this burst in a category by itself. It was not just the brightest gamma-ray burst of the year. It was not just the brightest of the decade. Early analysis suggested it was the brightest gamma-ray burst ever recorded since the phenomenon was first identified more than 50 years earlier. The informal name began circulating almost immediately. The BOT, the brightest of all time. To reconstruct the true brightness of the burst, scientists had to use indirect methods. The Fermi gamma-ray burst monitor had saturated, meaning its direct measurements were unreliable during the peak. But other instruments, designed for different purposes and with different sensitivity ranges, captured parts of the signal. The CONUS instrument aboard the WIND spacecraft, the gamma-ray detector on Integral, and observations from several other satellites provided overlapping but incomplete views. By combining these datasets, researchers were able to piece together a light curve, a graph of brightness over time, that revealed the full scale of the event. The burst arrived in stages. The initial pulse was followed by a brighter, more sustained emission phase that lasted roughly 600 seconds, or about 10 minutes. During the peak of this phase, the gamma-ray flux at Earth exceeded anything previously measured. The total fluence, the total energy per unit area received at Earth over the duration of the burst, was approximately 1 × 10 to the negative 2 ergs per square centimeter in the gamma-ray band alone. Written out, that is 1/100th of an erg per square centimeter. This may sound small, but for a source at cosmological distances, it is extraordinary. Most gamma-ray bursts deliver a fluence roughly 1,000 times smaller. The position of the burst was traced to a galaxy at a cosmological redshift of 0.151. Redshift is a measure of how much the wavelength of light has been stretched by the expansion of the universe during its journey. A redshift of 0.151 corresponds to a distance of approximately 2.4 billion light-years, or about 740 megaparsecs. In cosmic terms, this is not particularly far. Most gamma-ray bursts with measured distances lie at redshifts of 1 to 3, corresponding to distances of roughly 5 to 11 billion light-years. GRB 221009A was, by these standards, a relatively nearby event. This proximity certainly contributed to its record-setting brightness as observed from Earth, but it could not fully explain the magnitude of what was seen. The total energy released in gamma rays, calculated under the assumption that the burst radiated equally in all directions, which it almost certainly did not, but which provides a useful upper bound, was estimated at approximately 1 × 10 to the 54th ergs. To put this in context, the total energy output of the Sun over its entire lifetime is roughly 3.8 × 10 to the 53 ergs. The gamma-ray energy alone from this single burst was roughly 3 times the Sun's lifetime output, compressed into minutes, and this was only the gamma-ray component. Additional energy was carried by X-rays, by visible light, by radio waves, by neutrinos, by gravitational waves, and by the kinetic energy of the jet itself. The total energy budget of the event was significantly larger, but this calculation assumed the burst radiated in all directions, which we know is not the case. The energy was focused into a narrow jet. If the jet had an opening half angle of, say, 3.4 degrees, the actual total energy would be reduced by a factor of roughly 500 compared to the isotropic value. Even so, the corrected energy remained among the highest ever inferred for a gamma-ray burst. The jet of GRB 221009A was not merely bright, it was one of the most energetic jets ever produced by the death of a star. Here is where the core problem begins to crystallize. The standard model of long gamma-ray bursts, known as the collapsar model, was developed in the 1990s by astrophysicist Andrew McFadden and others, building on earlier ideas by Stanford Woosley. In this model, a rapidly rotating massive star collapses. Its core forms a black hole, an accretion disk forms around the black hole, and bipolar jets are launched. The model has been extraordinarily successful. It explains the general properties of long gamma-ray bursts, their durations, their spectra, their afterglows, and their association with a particular type of supernova called a Type IC, broad-lined supernova. But the model has limits. There is only so much energy available in the collapse of a stellar core. The gravitational binding energy of the core, the total energy released when it collapses, is roughly 3 × 10⁵ ergs. This sets a ceiling. Not all of this energy can go into the jet. Much of it goes into neutrinos, which carry away the vast majority of the energy. Some goes into the kinetic energy of the supernova ejector. Some goes into gravitational waves. The fraction that can be channeled into a relativistic jet is limited by the efficiency of the magnetic dynamo that powers the jet, by the mass of the accretion disk, and by the spin of the black hole. For most gamma-ray bursts, the energy in the jet is comfortably below this ceiling. It represents a small fraction of the available gravitational energy, and the physics works out neatly. For GRB 221009A, the energy budget was tight. The energy in the jet, even after correcting for the jet opening angle, approached the theoretical maximum. Either the burst was extremely efficient at channeling gravitational energy into a relativistic jet, more efficient than any burst previously observed, or the progenitor star provided an unusually large energy reservoir, or the jet geometry was different from what was assumed, or some combination of all three. And it gets worse. The afterglow of a gamma-ray burst is the slowly fading radiation produced as the jet decelerates in the surrounding medium. When the relativistic jet plows into the gas and dust between stars, called the interstellar medium, it creates a forward shock, a blast wave that sweeps up and heats the surrounding material. Electrons are accelerated to extreme energies at this shock front, and they emit radiation across the electromagnetic spectrum as they spiral in the magnetic fields behind the shock. This radiation follows predictable patterns. The brightness at different wavelengths and the rate at which the afterglow fades are determined by a handful of parameters: the energy of the jet, the density of the surrounding medium, the fraction of energy given to the electrons, the fraction given to the magnetic field, and the electron energy distribution. For decades, this standard afterglow model, known as the fireball model, has been remarkably successful. Plug in the right parameters, and it predicts the observed afterglow with impressive accuracy. But for GRB 221009A, the afterglow told a strange story. In the X-ray band, observed by Swift's X-ray telescope, the afterglow was the brightest ever recorded for a gamma-ray burst. It remained detectable for months, far longer than a typical afterglow. The X-ray light curve showed a power law decline, as expected, but with subtle features that did not perfectly match the simplest version of the fireball model. There were hints of energy injection, additional energy being pumped into the blast wave at late times, as though the central engine, the newborn black hole, continued to power the jet long after the initial burst had ended. The optical afterglow, the visible light component, was also remarkably bright. It was detectable by amateur astronomers with modest telescopes, an unusual feat for a gamma-ray burst at 2.4 billion light-years. But the optical brightness, strangely, was not as extreme relative to the X-ray brightness as the standard model predicted. There appeared to be a suppression of optical light. The leading explanation was dust. The burst occurred within its host galaxy, and spectroscopic observations revealed significant absorption by dust along the line of sight. This dust absorbed much of the optical and ultraviolet light, while allowing higher energy X-rays to pass through relatively unimpeded. The result was an afterglow that appeared dimmer in visible light than its X-ray brightness would suggest. The radio afterglow added another layer of complexity. Radio telescopes around the world, including the Carl G. Jansky Very Large Array in New Mexico, the Meerkat Array in South Africa, the Atacama Large Millimeter Array in Chile, and numerous other facilities, monitored the fading radio signal for months and eventually years. The radio emission from a gamma-ray burst afterglow provides information about the jet that is difficult to obtain at other wavelengths. In particular, the late-time radio behavior can reveal the geometry of the jet. When a relativistic jet decelerates, it gradually spreads sideways. Initially, when the jet is moving close to the speed of light, relativistic beaming confines the observable emission to a narrow cone. As the jet slows, this cone widens, and eventually the observer can see the full extent of the jet. This produces a characteristic steepening in the afterglow light curve, known as the jet break. The time at which the jet break occurs tells us the opening angle of the jet. A narrow jet, covering a small area of the sky, produces an early jet break. A wide jet produces a late one. For GRB 221009A, the jet break was frustratingly difficult to pin down. Different teams analyzing different wavelengths reported different answers. Some analyses of the X-ray data suggested the jet break occurred at roughly 1 to 2 days after the burst, implying a relatively narrow jet with an opening half angle of around 3 to 4 degrees and a total corrected energy that, while high, was within the bounds of existing models. Other analyses, particularly those using later radio observations, suggested the jet break came much later, at 10 days or more, implying a wider jet of perhaps 7 to 10 degrees and a correspondingly higher total energy. The discrepancy was not a minor academic disagreement. The total energy of the burst scales roughly as the square of the jet opening angle. If the angle was twice as large, the energy was 4 times as great. The difference between the narrow jet and wide jet interpretations represented a factor of 10 or more in the estimated total energy. At the upper end, the energy requirements became deeply uncomfortable for the collapsar model. The progenitor star would need to have been extraordinarily massive, perhaps 70 or 80 solar masses or more, and the efficiency of converting gravitational collapse into a focused jet would need to have been near the theoretical maximum. Part of the difficulty lay in the jet's structure. The afterglow data suggested that the jet was not a simple uniform cone, the so-called top hat jet. Instead, it appeared to have a structured profile, brightest and most energetic along its central axis, gradually decreasing in power toward its edges. Think of the beam from a flashlight. A cheap flashlight might produce a relatively uniform circle of light with a hard edge. A high-quality flashlight produces a bright hotspot in the center, surrounded by a gradually dimming halo. The jet of GRB 221009A appeared to be more like the second type. This structured jet complicated everything. The apparent brightness depended not just on the total jet energy and the observer's distance, but also on the precise angle between the jet axis and the line of sight. If Earth was positioned almost exactly along the central axis of the jet, the observed brightness was maximized. Even a slight misalignment, even a fraction of a degree, would significantly reduce the apparent intensity. This meant the extraordinary brightness might have been partly a geometric accident. The burst was not only relatively nearby, but also viewed from an angle that happened to maximize its apparent luminosity. This is a plausible explanation, but it introduces a new improbability. The probability of a burst occurring this close to us is one factor. The probability of being aligned with the brightest part of a structured jet is another. The combined probability is very small, suggesting either remarkable coincidence or a flaw in the statistical models used to estimate burst rates. Then there were the very high-energy photons. The Fermi Large Area Telescope detected photons from this burst, with energies exceeding tens of billions of electron volts. And the Large High-Altitude Air Shower Observatory, LHAASO, located at an altitude of 4,410 meters in China's Sichuan province, detected photons with energies reaching approximately 18 tera-electron volts, or 18 trillion electron volts. These were among the most energetic photons ever recorded from any astrophysical source, and the most energetic ever from a gamma-ray burst. But here's the problem. Photons at these energies face a formidable obstacle during their journey through intergalactic space. The universe is pervaded by a diffuse bath of low-energy photons, mostly infrared and optical light, produced by every star and galaxy that has ever shone. This is called the extragalactic background light, or EBL. When a very high-energy gamma-ray photon collides with one of these ambient photons, the two can annihilate, converting their energy into a pair of particles, an electron and its antimatter twin, a positron. This process, called pair production, effectively absorbs very high-energy gamma rays over cosmological distances. The farther the photon travels, the higher the probability that it will be annihilated before reaching us. For a source at 2.4 billion light-years, The universe is substantially opaque to photons at energies above a few tera-electron volts. The optical depth, a measure of the absorption, increases steeply with photon energy. At 18 tera-electron volts, only a small fraction of the emitted photons should survive the journey. The detection of photons at this energy by Lahazo therefore implied one of several things. The first possibility was that the source was producing very high energy photons in truly enormous quantities. If only 1 in 100 or 1 in 1,000 photons survived the trip, then the total number produced must have been correspondingly huge, implying an energy output at very high energies that was difficult to accommodate even with optimistic models. The second possibility was that our understanding of extragalactic background light was wrong. If the universe contained fewer ambient photons than models predicted, the absorption would be less severe, and more high-energy photons would survive. But the EBL has been measured and modeled by multiple independent groups using multiple independent techniques, and the consensus models are considered fairly reliable. A major revision of the EBL would have implications far beyond gamma-ray bursts, affecting our understanding of the total light output of all galaxies in cosmic history. The third possibility, the most exotic, was that some new physics was at work. In certain theories of quantum gravity, the structure of space-time at the smallest scales might cause very high-energy photons to travel at slightly different speeds than lower-energy photons, or to interact with the background light in a slightly different way. This is called Lorentz invariance violation, and it would represent a departure from one of the foundational principles of Einstein's special relativity. If the interaction cross-section for pair production was slightly reduced at extreme energies, more photons would survive the journey, explaining the Hazo detection without requiring an impossibly powerful source or a faulty EBL model. Each of these explanations carried profound implications. The first meant the burst was even more energetic than the lower energy observations indicated. The second meant our model of the total light in the universe was flawed. The third meant the fundamental structure of spacetime was different from what Einstein described. None of these options were comfortable. None were easy to confirm or rule out with the available data. Something is wrong with our assumptions. That was the quiet realization spreading through the astrophysics community in the months following the burst. Not wrong in the sense of a complete failure. The basic picture of a collapsing star forming a black hole and launching relativistic jets was almost certainly correct. The afterglow behaved, broadly speaking, as the fireball model predicted. The host galaxy was the right kind of galaxy. The burst's location within the galaxy was consistent with a star-forming region, exactly where massive stars live and die. But the details, the extreme energy, the structured jet, the very high-energy photons, the saturated instruments, all of these pushed against the boundaries of what had been considered possible. In the months following the burst, over 150 scientific papers were published analyzing different aspects of the event. Entire conference sessions were dedicated to it. Teams at observatories on every continent raced to extract every available photon of information from the data. The debate over the jet opening angle continued. The debate over the true energy continued. The debate over the very high energy emission continued. The search for the associated supernova became one of the most closely watched follow-up campaigns in recent memory. According to the collapsar model, every long gamma-ray burst should be accompanied by a supernova, specifically a Type IC broadline supernova, caused by the explosive ejection of the star's outer layers as the core collapses. Previous well-studied gamma-ray bursts, such as GRB 980425, had been clearly associated with such supernovae, providing strong evidence for the collapsar picture. For the brightest of all time, the supernova should have been visible roughly 2 to 3 weeks after the burst, emerging from beneath the fading afterglow as a slowly brightening bump in the optical light curve. But finding that supernova was enormously difficult. The afterglow of GRB 221009A was itself so luminous that it overwhelmed the expected supernova signal. This is like trying to spot a candle flame while someone is pointing a searchlight in your eyes. The searchlight must fade enough for the candle to become visible. Compounding this difficulty was the dust in the host galaxy. The burst occurred behind a substantial column of interstellar dust within its host, which preferentially absorbed optical and ultraviolet light while allowing X-rays and infrared to pass. The supernova, which radiates primarily in the optical and near-infrared, was therefore dimmed by this dust screen. Teams around the world attempted the search using the largest optical and infrared telescopes available. The Hubble Space Telescope observed the location multiple times, seeking the supernova signature in the ultraviolet and optical bands. Ground-based observatories with adaptive optics systems, which correct for the blurring effects of Earth's atmosphere, stared at the fading afterglow night after night. But the critical breakthrough came from an instrument that had not even been designed with gamma-ray bursts in mind. The James Webb Space Telescope, launched in December of 2021 and still in its early operational phase in late 2022, turned its infrared eye toward the location of the burst. Operating at wavelengths from 1 to 28 micrometers, Webb could peer through the dust that obscured the optical view. Its observations, obtained several weeks after the burst, provided tentative evidence for a supernova component emerging from the declining afterglow. The supernova appeared consistent with the Type IC broad-lined event, as the collapsar model predicted, but it was not dramatically brighter than supernovae associated with less energetic gamma-ray bursts. This was puzzling. If the jet was the most powerful ever observed, one might expect the supernova to be comparably extreme. Instead, the supernova was unremarkable. This suggested an important subtlety in the physics. The jet energy and the supernova energy may be drawn from partially independent sources. The jet is powered by the accretion disk around the black hole and the magnetic fields that thread it. The supernova is powered primarily by the radioactive decay of nickel-56, produced in the explosive nucleosynthesis during the collapse and ejection. A more powerful jet does not necessarily mean more nickel-56 was produced. The two energies are related, since they both originate in the collapse of the same star, but they are not rigidly coupled. This decoupling had been suggested theoretically, but had never been observed so clearly in a single event. GRB 221009A provided one of the strongest pieces of evidence that the jet and the supernova tap different aspects of the collapse, and that the most extreme jets do not require the most extreme supernovae. Meanwhile, the observing campaign continued to expand. Radio telescopes provided a particularly valuable window. Radio waves, with wavelengths ranging from millimeters to meters, are largely unaffected by dust and can penetrate through the interstellar medium with minimal absorption. Radio observations of the afterglow probed the physics of the decelerating blast wave at late times, long after the X-ray and optical afterglows had faded to faint shadows of their former selves. The Meerkat Radio Telescope in South Africa's Karoo region, consisting of 64 dish antennas each 13.5 meters in diameter, tracked the radio afterglow for over a year. The Jansky Very Large Array in New Mexico, with its 27 antennas spread across the desert in a Y-shaped configuration, provided complementary observations at different radio frequencies. The Atacama Large Millimeter Array in Chile, perched at an altitude of 5,000 meters in the Atacama Desert, observed the afterglow at millimeter wavelengths, bridging the gap between radio and infrared. The combined radio dataset revealed the evolving structure of the blast wave as it expanded and decelerated. Early radio observations showed scintillation, rapid fluctuations in brightness caused by the blast wave being small enough that turbulence in the interstellar medium of our own galaxy affected the incoming radio signals, the same effect that makes stars twinkle in the optical. As the blast wave expanded, the scintillation decreased, providing an independent measure of the blast wave's physical size. By comparing the blast wave's size at different times with its observed brightness, researchers could constrain the energy and geometry of the jet. The picture that emerged was consistent with a structured jet viewed near its axis, but the detailed parameters depended on which dataset was given the most weight, and different groups reached somewhat different conclusions. The uncertainty was not a failure of the data, it was a reflection of the complexity of the event. The burst was so energetic, so well observed and so rich in detailed structure that it exceeded the ability of simple models to fully capture its behavior. More sophisticated models, incorporating jet structure, sideways expansion, energy injection from the central engine, and the effects of the surrounding medium, were required. And even these more complex models left residuals, discrepancies between prediction and observation that pointed to physics not yet fully understood. This is how science advances, not by confirming existing models with expected observations, but by finding events so extreme that the models break, revealing the assumptions hidden within them. GRB 221009A was precisely such an event. It was the stress test that the gamma-ray burst community had never had, and it exposed joint and seam in the theoretical framework. The global response was unprecedented. Over 150 papers were published in the first year alone, analyzing different aspects of the event. Special issues of major astronomy journals were dedicated to it. Conference sessions spanning multiple days were organized. Competing theoretical interpretations were debated with an intensity that had not been seen in the gamma-ray burst community for decades. The event reinvigorated a field that some had considered mature, showing that even after 50 years of study, the universe could still surprise. And beneath all of these specific debates, a more fundamental question lingered. Was GRB 221009A simply a statistical outlier, a once-in-10,000-year event that happened to occur during the brief window of human technological capability to observe it? Or was it revealing something about the physics of gamma-ray bursts that less extreme events had failed to expose? Were our models, built on observations of thousands of ordinary bursts, missing something that only became visible when the universe turned the dial to its maximum setting? The implications of that question extended beyond astrophysics. Because if the universe can produce events of this magnitude, even rarely, then the assessment of the threat posed by gamma-ray bursts to life in the cosmos, including life on Earth, might need to be reconsidered. Not in the sense of immediate danger, not in the sense of panic, but in the sense of a quiet, careful recalculation of the odds. But here's what makes this truly terrifying. To fully grasp why GRB 221009A sent shockwaves through the scientific community, we need to examine the different approaches researchers took to understand it, the theories they tested, and the places where those theories bent, strained, or broke entirely. Because this burst was not just a record-setting observation. It was a test of the models that astrophysicists had spent decades building, and some of those models did not pass. The first approach was the most straightforward. Treat the burst as an ordinary gamma-ray burst that happened to appear very bright because it was relatively close. This is the proximity argument. Most gamma-ray bursts detected by Fermi and Swift occur at distances of 5 to 10 billion light-years or more. At those distances, only the most powerful bursts produce enough photons to trigger our detectors. GRB 221009A, at 2.4 billion light-years, was closer than roughly 95% of all gamma-ray bursts with measured distances. So perhaps it appeared extraordinary simply because it was near. The way a campfire looks like a bonfire when you are standing close to it. The mathematics of this argument are straightforward but revealing. The apparent brightness of any source, the flux of energy arriving at the detector, decreases with the square of the distance. If you double the distance, the brightness drops to 1/4. If you halve the distance, the brightness increases by a factor of 4. GRB 221009A was perhaps 3 to 5 times closer than a typical gamma-ray burst. That geometric advantage would make it appear roughly 9 to 25 times brighter than an identical burst at a more typical distance. But the observed brightness was not just 9 or 25 times greater than average. It was hundreds of times greater. By some measures involving peak flux, it was thousands of times brighter than what would be expected from even a reasonably energetic burst at this distance. Proximity helped, certainly, but it could not explain the full magnitude. The campfire was not ordinary. Even standing right next to it, you would know this was not a normal fire. Statistical analysis confirmed the conclusion. Researchers examined the full catalogue of gamma-ray bursts detected over the past 5 decades, encompassing thousands of events. They asked a straightforward question. Given the known distribution of gamma-ray burst energies and the known distribution of burst distances, how often would we expect to observe a burst this bright from Earth? The answer varied depending on assumptions about the underlying energy distribution, but most analyses converged on a range between once per 1,000 years and once per 10,000 years. The most commonly cited figure was roughly once per 10,000 years. This is where the statistics become almost philosophical. The universe has been producing gamma-ray bursts for billions of years. Humanity has been capable of detecting them for only about 55 years, starting with the Vela satellites in the late 1960s. If the expected rate of a burst this bright is once per 10,000 years, then the probability of observing one during a 55-year window is roughly 5.5 in 10,000, or about 0.055%, less than 1/10 of 1%. The fact that we caught it was either an extraordinary coincidence, the kind of low probability event that must happen sometimes simply because low probability events do happen, or it was evidence that the statistical model was wrong. Perhaps bursts this bright occur more often than the models predicted. Perhaps the tail of the energy distribution was heavier than assumed. This remains an open question. The second approach focused on the geometry of the jet. As described earlier, gamma-ray burst jets are not uniform beams of constant brightness. The standard model used for decades was the top hat jet, a cone of uniform intensity with sharp edges. Within the cone, the brightness is the same everywhere. Outside the cone, it drops to zero. This model is mathematically simple and has been applied successfully to many bursts. For GRB 2210009A, the top hat model struggled to accommodate all the observations. A team led by Brendan O'Connor, along with other independent groups using data from multiple telescopes spanning radio through X-ray wavelengths, found that the afterglow behavior was better explained by a structured jet. In this model, the jet has a bright, energetic core surrounded by progressively less energetic wings. The energy per unit solid angle is highest along the central axis and decreases smoothly toward the edges, following a power law or a Gaussian profile. The implications of a structured jet are significant. If Earth happened to be positioned almost directly along the jet's central axis, looking straight down the barrel, the observed brightness would be at its theoretical maximum. Even a slight misalignment, a displacement of just a fraction of a degree from the axis, would place the observer in a region of lower energy per solid angle, reducing the apparent brightness significantly. The extraordinary brightness of GRB 221009A might therefore have been partly an accident of geometry. We happen to be looking along the brightest possible line of sight. This is plausible, but it compounds the improbability rather than resolving it. The probability of a gamma-ray burst occurring within 2.4 billion light-years is already low, perhaps once per century or per millennium, depending on the energy threshold. The probability of that burst's jet axis being aligned with Earth to within a fraction of a degree is an additional factor, perhaps 1 in several thousand. The product of these two probabilities is extremely small. The burst was nearby and perfectly aimed. Each condition alone is rare. Together, they are rarer still. Several groups attempted to constrain the viewing angle using the afterglow data. The relative brightness at different wavelengths, the shape of the light curves, and the evolution of the radio emission all carry information about the observer's position relative to the jet. The results were tantalizing, but not conclusive. Best fit models generally placed the viewing angle within 1 to 2 degrees of the jet axis, consistent with a nearly on-axis observation. But the uncertainties were large enough to allow a range of solutions, and different datasets favored slightly different geometries. The numbers are striking. Consider this. If the jet had a core half angle of about 1.7 degrees, the solid angle of the core would be approximately 2.8 times 10 to the negative 3 steradians, or about 1/4500th of the full sky. This means that for any given gamma-ray burst, the probability of being within the core is less than 1/10 of 1%. Combined with the proximity factor, the probability of observing an event like this becomes vanishingly small, consistent with the once per 10,000 year estimate, but also unsettling. We were, in a very real sense, staring down the barrel of a cosmic gun. The third approach attempted to understand the progenitor star itself. What kind of star could produce a jet of such extraordinary power? The collapsar model requires a massive, rapidly rotating star that has lost its outer hydrogen envelope. These are Wolf-Rayet stars, among the most extreme objects in any galaxy. They are hot, with surface temperatures exceeding 50,000 degrees Celsius. They are luminous, outshining the sun by factors of hundreds of thousands to millions. And they are unstable, shedding mass at prodigious rates through powerful stellar winds that strip away their outer layers over millions of years. A Wolf-Rayet star destined to produce a gamma-ray burst must satisfy several stringent conditions. It must be massive enough, typically exceeding 25 solar masses at the time of core collapse, to form a black hole rather than a neutron star. It must be rotating rapidly enough that the infalling material forms a thick accretion disk rather than falling directly into the black hole. And ideally, it should have relatively low metallicity, meaning it contains few elements heavier than helium, because metals drive stronger stellar winds, which carry away angular momentum and slow the star's rotation. For GRB 221009A, the progenitor was likely exceptional even by the standards of gamma-ray burst progenitors. To produce a jet with the observed energy, the star probably had an initial mass exceeding 40 solar masses, and possibly 60 to 80 or more. The mass of the resulting black hole was estimated at perhaps 5 to 15 solar masses. The accretion rate onto the black hole, the rate at which material from the disk fell inward and powered the jet, must have been high and sustained for several hundred seconds to produce the observed duration of the burst. Some models went further. They suggested that the progenitor might have been in a binary system, a pair of massive stars orbiting each other. Interactions between the two stars, such as mass transfer or tidal forces, could have spun up the progenitor to the rapid rotation rates needed for jet formation. Alternatively, the progenitor might have merged with a companion star at some point during its evolution, gaining both mass and angular momentum. These scenarios are speculative, but they provide mechanisms for producing the extreme conditions that the burst seems to require. But here's the problem. We cannot directly observe the progenitor star. It no longer exists. It destroyed itself in the act of creating the burst. All we can observe are the consequences, the burst itself, the afterglow, and the associated supernova. For GRB 221009A, the expected supernova was a key test. If the burst was produced by a collapsing massive star, as the collapsar model requires, then a supernova should have been visible in the optical afterglow, emerging as a bump in the light curve a few weeks after the burst as the expanding supernova ejector became visible. Astronomers searched intensively for this supernova signature. The task was difficult. The afterglow of the burst itself was extremely bright, and the supernova signal had to be separated from the fading afterglow. Moreover, the significant dust absorption in the host galaxy dimmed the optical light, making the supernova harder to detect. Initial reports were contradictory. Some groups reported marginal evidence of a supernova component. Others found that the optical light curve could be explained entirely by the afterglow without needing a supernova. Eventually, analysis using the James Webb Space Telescope, which observed the location of the burst in the infrared where dust absorption is less severe, provided evidence for a supernova component consistent with a Type IC broad-lined supernova, similar to those associated with other gamma-ray bursts, but perhaps somewhat fainter than expected. Given the extraordinary energy of the burst, this was not necessarily a contradiction, but it was puzzling. One might expect the most energetic gamma-ray burst to be accompanied by the most energetic supernova. Instead, the supernova appeared to be broadly normal, suggesting that the jet and the supernova might be somewhat decoupled, drawing their energy from partially independent reservoirs. The fourth approach examined the very high energy emission in detail, seeking to understand the physical mechanism that produced the 18 tera electron volt photons detected by LAHAZO. This is where the physics becomes particularly challenging. In the standard synchrotron model, electrons accelerated at the shock front spiral in the magnetic field behind the shock and emit radiation. The energy of the emitted photons depends on the energy of the electrons and the strength of the magnetic field. There is a fundamental upper limit to the photon energy that synchrotron radiation can produce, known as the burn-off limit. This limit arises because the highest energy electrons lose energy so rapidly through radiation that they cannot be accelerated to higher energies. For typical gamma-ray burst parameters, the synchrotron burn-off limit is in the range of hundreds of millions of electron volts. The detected photons at 18 tera electron volts exceeded this limit by a factor of roughly 100,000. The standard resolution to this problem is inverse Compton scattering. In this process, a high-energy electron collides with a lower-energy photon, a synchrotron photon, for example, and transfers a large fraction of its energy to the photon, boosting the photon to much higher energy. This synchrotron self-Compton process can produce photons at energies well above the synchrotron burn-off limit, potentially reaching the tera-electron volt range. The efficiency of this process depends on the number and density of both electrons and synchrotron photons in the emission region, as well as the Lorentz factor of the jet. For GRB 221009A, synchrotron self-Compton models could, in principle, produce photons at the observed energies, but the models required the emission region to be compact and densely populated with both electrons and photons, conditions that pushed the parameters to extreme values. The magnetic field had to be relatively weak compared to the energy in the electrons, a condition that differs from the near equipartition typically assumed. The Lorentz factor of the jet had to be high, several hundred at minimum, and the total energy in the very high energy component had to be a significant fraction of the total burst energy. Some researchers explored alternative emission mechanisms. Could the very high energy photons come from hadronic processes involving protons rather than electrons? In these models, protons accelerated at the shock front, interact with ambient photons or other protons to produce pions, which then decay into gamma rays and other particles. Hadronic processes can produce very high energy gamma rays without the synchrotron burn-off limitation, but they are generally less efficient than leptonic processes and require even higher total energies. For a burst that was already straining the energy budget, hadronic models seemed difficult to accommodate. Others explored the possibility that the very high-energy photons were produced not by the external shock, where the jet hits the surrounding medium, but by the internal dissipation processes within the jet itself. If magnetic reconnection events within the jet could accelerate particles to extreme energies, the resulting radiation might reach the tera-electron volt range. This scenario was less constrained by the afterglow parameters, but introduced its own set of assumptions about the internal structure of the jet. The absorption of very high-energy photons by the extragalactic background light added a further complication. At 18 tera-electron volts, the optical depth for pair production over 2.4 billion light-years is substantial, meaning a large fraction of the emitted photons at this energy would be absorbed before reaching Earth. The survival probability depends on the precise density and spectrum of the EBL, which is known to reasonable but not perfect accuracy. If the actual EBL density along the line of sight to the burst was at the lower end of the model uncertainties, more photons would survive, easing the energy requirements at the source. If it was at the upper end, fewer would survive, and the source would need to be correspondingly more powerful. The Lhasa observations prompted a renewed interest in using very high-energy observations of distant sources to probe the EBL. Every very high-energy photon, detected from a cosmological source, is a data point constraining the opacity of the universe. GRB 221009A, with its well-measured distance and extreme photon energies, provided one of the most sensitive probes of the EBL ever obtained. The data were broadly consistent with existing EBL models, suggesting no dramatic revision was needed, but the constraints were tight enough to disfavor some of the higher estimates. The speculative possibility of Lorentz invariance violation remained in the discussion, but at the margins. The data from GRB 221009A alone could not conclusively demonstrate or rule out such effects. What it did was add to a growing body of observations that constrained the energy scale at which Lorentz invariance might break down, pushing it to higher values and making it harder for quantum gravity theories that predict low-scale violations to survive. The fifth and perhaps most viscerally striking approach examined the effect of the burst on Earth itself. The gamma rays from GRB 221009a, after traveling for 2.4 billion years through expanding space, arrived at Earth and passed through the atmosphere. The atmosphere is not transparent to gamma rays. High-energy photons interact with atmospheric molecules, initiating cascades of secondary particles. The gamma rays from the burst were absorbed high in the atmosphere, depositing their energy primarily in the ionosphere, the layer of charged particles between about 60 and 1,000 kilometers altitude. The ionosphere is maintained by solar ultraviolet radiation during the day and decays at night as ions and electrons recombine. It is a critical component of Earth's radio communication infrastructure. Very low-frequency radio waves, with frequencies between 3 and 30 kHz, propagate through the waveguide formed between the ionosphere and the Earth's surface. Changes in the ionosphere alter the propagation characteristics of these waves, and monitoring stations around the world continuously measure these changes. At the time the burst arrived at Earth, monitoring stations in India, operated by a group that had been measuring very low-frequency signals for years, detected a sudden disturbance. The ionization in the D layer of the ionosphere, at an altitude of roughly 60 to 90 kilometers, increased abruptly. The perturbation was consistent with a sudden influx of X-ray and gamma-ray photons ionizing the upper atmosphere, exactly what the burst would produce. The effect lasted several minutes and then faded as the ionization returned to its normal level. The magnitude was comparable to a moderate solar flare, the kind of event that is not dangerous but is easily detectable. This was the first unambiguous detection of a gamma-ray burst affecting Earth's ionosphere. Previous bursts had been too distant or too faint to produce a measurable effect. The proximity and extreme brightness of GRB 221009a made it the first to cross the threshold. A pulse of radiation from a dying star 2.4 billion light-years away had briefly altered the electrical properties of our planet's upper atmosphere. The event was harmless, but the principle it demonstrated was not harmless at all. Consider what would have happened if this same burst had occurred not at 2.4 billion light-years, but at a distance of 100 light-years, roughly the distance to some of the nearer bright stars in our galaxy. The intensity of the radiation scales inversely with the square of the distance. Reducing the distance from 2.4 billion light-years to 100 light-years is a factor of 24 million. The intensity would increase by the square of that factor, roughly 5.8 times 10 to the 14th, or about 580 trillion times brighter. At that intensity, the gamma-ray flux would not merely tickle the ionosphere, it would shatter it. The ozone layer, which absorbs much of the harmful ultraviolet radiation from the sun and makes life on Earth's surface possible, would be severely depleted. The gamma rays and X-rays would dissociate molecular nitrogen and oxygen in the upper atmosphere, producing nitrogen oxides that catalytically destroy ozone. Models suggest that a gamma-ray burst at a distance of roughly 100 to 1,000 light-years could deplete 30 to 50% of the ozone layer. The effects would persist for years, as the nitrogen oxides are relatively long-lived in the stratosphere. During that time, the surface of the Earth would be bathed in elevated levels of solar ultraviolet radiation, causing widespread damage to photosynthetic organisms, disrupting marine food chains, increasing mutation rates, and potentially triggering a mass extinction. Even at a distance of several thousand light-years, the effects might be significant. The ozone depletion would be less severe, perhaps 10 to 20%, but still enough to measurably increase ultraviolet radiation at the surface. For organisms with limited ability to shield themselves, such as plankton near the ocean surface, even this moderate increase could be devastating. A sixth consideration, closely related to the fifth, concerns the broader question of how frequent such threats have been over Earth's history. The galaxy has been forming stars for roughly 12 billion years. In that time, Countless massive stars have lived and died, and some fraction of them have produced gamma-ray bursts. The rate of gamma-ray bursts in the Milky Way is estimated at roughly 1 per several 100,000 to 1 million years. Most of these bursts, because of the narrow jet opening angle, would not be aimed at Earth. The rate of bursts aimed at us might be once per 100 million to a few 100 million years. But in 4.5 billion years, the Earth has gone through many such intervals. The probability that at least one gamma-ray burst has been aimed at Earth during the history of life on this planet is not negligible. Some researchers estimate it at 50% or higher, depending on assumptions about burst rates and jet angles. The Ordovician-Silurian mass extinction, roughly 445 million years ago, has been proposed as a candidate event, though the evidence is circumstantial. The pattern of extinction, preferentially affecting shallow water marine organisms while sparing deep water species, is consistent with elevated ultraviolet radiation caused by ozone depletion. But correlation is not causation, and other explanations, including glaciation and ocean chemistry changes, can also account for the pattern. What GRB 221009A provided was not new risk, but new context for understanding old risk. It showed that the universe produces events at the extreme end of the energy distribution, events that exceed the predictions of standard models. If the tail of the distribution is heavier than assumed, the rate of truly catastrophic events might be slightly higher than previous estimates suggested. Not dramatically higher, not high enough to change the immediate risk calculus, but enough to shift the conversation, to move the threat from a theoretical curiosity to a measured reality. Each of these approaches, proximity, jet geometry, progenitor physics, very high energy emission, ionospheric effects, and extinction risk, revealed a different facet of the boat, and each, in its own way, found limits. The proximity argument explained part of the brightness but not all. The structured jet model introduced new uncertainties. The progenitor physics required extreme conditions. The very high energy emission strained known mechanisms. The ionospheric detection demonstrated a new sensitivity to cosmic events. And the extinction calculations reminded us that the universe's indifference operates on all timescales, including those that matter to biology. Let us pause for a moment and take stock of what the proximity argument, the jet geometry, and the progenitor physics all share. Each of them, in its own way, is an attempt to explain the extraordinary by invoking the rare. The burst was bright because it was close. The burst was bright because we were perfectly aligned with the jet axis. The burst was bright because the progenitor star was among the most massive and rapidly rotating that nature can produce. Each explanation is plausible, each is supported by some of the data, and each requires conditions that are, by definition, unusual. The question is whether one unusual condition is enough, or whether we need all of them simultaneously, which would make the event so improbable as to challenge our statistical models. There is a useful framework for thinking about this. In probability theory, the occurrence of an event that appears extremely unlikely under a given model can mean one of two things. Either the model is correct and we happen to observe a rare fluctuation, or the model is wrong and the event is not as unlikely as it seems. Distinguishing between these two possibilities requires more data, either more events like this one or more precise measurements of the existing event. For GRB 221009A, we have one event and a large but finite amount of data. The debate will continue until either a comparable burst is observed or theoretical advances provide a more definitive framework. In the meantime, there is another angle that deserves exploration: the burst as a probe of fundamental physics. This is the fourth dimension of the investigation, and it carries implications that extend far beyond astrophysics. The speed of light in a vacuum is one of the most fundamental constants in physics. It is the same for all observers, regardless of their motion. It does not depend on the wavelength or energy of the photon. A gamma-ray photon traveling at 18 tera-electron volts moves at exactly the same speed as a radio wave photon, with an energy billions of times lower. This is the principle of Lorentz invariance, and it is a cornerstone of Einstein's special theory of relativity, which has been tested to extraordinary precision in laboratories and particle accelerators. but there are theoretical reasons to suspect that at sufficiently extreme energies approaching the Planck scale of roughly 10 to the 19th giga electron volts, Lorentz invariance might break down. Some theories of quantum gravity, which attempt to unify general relativity with quantum mechanics, predict that spacetime has a discrete, granular structure at the Planck length, roughly 1.6 times 10 to the negative 35 meters. This graininess could cause very high-energy photons to travel at slightly different speeds than lower-energy photons, an effect so tiny that it would be completely undetectable in any laboratory, but that might accumulate over cosmological distances. GRB 221009A, with its very high-energy photons traveling 2.4 billion light-years, provided an exceptional test of this idea. The principle is simple. If high-energy photons travel even slightly faster or slower than low-energy photons, the high-energy photons from the burst would arrive at Earth at a slightly different time than the low-energy photons. By comparing the arrival times of photons at different energies, researchers could search for a speed difference and thereby constrain or detect Lorentz invariance violation. The analysis was performed by several groups using data from Fermi and Hazo. The results showed no significant evidence of energy-dependent photon speed. The arrival times of photons at different energies were consistent with all photons traveling at the same speed, as standard physics predicts. This null result pushed the constraints on the energy scale of potential Lorentz invariance violation to higher values, above roughly 10 times the Planck energy in some models, further tightening the bounds on quantum gravity theories that predict such effects. This is a case where not finding something is itself a significant finding. The absence of Lorentz invariance violation in the data from the most powerful gamma-ray burst ever observed tells us that space-time, to the best of our ability to measure, behaves exactly as Einstein described, even for photons with energies in the trillions of electron volts, traveling for billions of years. The fabric of space is smooth, or at least smoother than some theories predicted. This constrains the space of possible quantum gravity theories and narrows the search for the ultimate theory of space-time. Beyond Lorentz invariance, the very high-energy photons from the burst were used to study another aspect of fundamental physics: the density of the extragalactic background light. The EBL is a faint, diffuse glow that permeates the universe, composed of all the light emitted by all the stars and galaxies throughout cosmic history. Measuring the EBL directly is extremely difficult because it is faint and because foreground sources, such as zodiacal light from dust in our own solar system, contaminate the measurement. But the EBL can be measured indirectly by observing how it absorbs very high-energy gamma rays from distant sources. Every very high-energy photon that travels through the universe has a probability of being absorbed by the EBL, and this probability depends on the density and spectrum of the EBL along the line of sight. By measuring how many very high-energy photons survive the journey from a source at a known distance, astronomers can infer the density of the EBL. The more photons that arrive, the lower the EBL must be, and vice versa. GRB 221009A, with its known distance of 2.4 billion light-years and its well-measured spectrum extending to 18 tera-electron volts, provided one of the most sensitive probes of the EBL at its distance. The data were consistent with current models of the EBL, which are based on counts of galaxies and their luminosities. This agreement was reassuring, suggesting that our census of the total light produced by all galaxies in the universe is approximately correct. But it also left little room for hidden sources of light, such as contributions from the first generation of stars or from decaying dark matter particles, both of which have been speculated to contribute to the EBL at some level. In other words, the boat tested our understanding not only of gamma-ray bursts, but of the entire history of light production in the universe. It confirmed, within the measurement uncertainties, that we have a reasonably accurate picture of how much light all the stars in all the galaxies have collectively produced over the past 13 billion years. That is a remarkable piece of knowledge, derived from the observation of a single dying star 2.4 billion light-years away. There is a seventh consideration that threads through all the others, and it concerns what GRB 221009A tells us about the instruments themselves. The burst saturated the Fermi gamma-ray burst monitor. It overwhelmed detectors on multiple satellites. It produced signals so intense that standard data analysis pipelines, designed for typical bursts, could not handle them. In the aftermath, new analysis methods had to be developed. Raw data had to be reprocessed using techniques that had never been needed before. Dead time corrections, accounting for the periods when the detectors were recovering from the overload of each photon, had to be applied with unprecedented care. This forced the instrument teams to understand their detectors at a deeper level than before. The saturation effects, the dead time characteristics, the nonlinear responses at extreme count rates, all of these had to be characterized and corrected. The result was a set of calibration improvements that will benefit the analysis of future bursts, even ordinary ones. The boat made us better at measuring the sky. No single framework fully explained GRB 221009A. No model could comfortably accommodate all the observations simultaneously. The burst sat at the extreme tail of every distribution, in a region of parameter space where data is sparse and uncertainty is enormous. It was a reminder that our understanding of the universe is built on the typical, and the universe is not always typical. Beneath the debates about jet angles and energy budgets and tera-electron-volt photons, there lies a truth that is both simpler and more profound than any technical argument. The universe is capable of violence on a scale that has no parallel in human experience. We live on a small planet, orbiting an average star in the outer suburbs of a galaxy that contains hundreds of billions of other stars. We have existed as a species for perhaps 300,000 years, a span so brief that if the history of the universe were compressed into a single calendar year, all of recorded human civilization would occur in the last fraction of the last second before midnight on December 31st. And during that fraction of a second, the universe produced the most luminous event ever recorded by our instruments. Let that sink in. The light from GRB 221009A began its journey approximately 2.4 billion years ago. At that time, Earth existed, but it was a world that no human would recognize. The planet was in the middle of the Proterozoic Eon, a vast stretch of geological time dominated by single-celled organisms. The most complex life forms were bacterial mats, and perhaps the earliest stirrings of multicellular algae. No animal had ever drawn breath. No eye had ever opened. The continents were arranged in configurations that geologists call Nuna or Columbia, a people supercontinent that was beginning to break apart. The atmosphere contained far less oxygen than it does today. The oceans were chemically different. The sky was a different shade. Everything was different. The photons that reached Fermi's detectors on that October day had been traveling through expanding space for that entire immense duration. They crossed voids between galaxy clusters, regions of near-perfect emptiness stretching millions of light-years across. They threaded through the vast cosmic web of dark matter and gas that connects galaxies like strands in a spider's web. They lost energy to the expansion of the universe, their wavelengths stretching as space itself expanded, a cosmological redshift that scientists measured precisely at 0.151. During their journey, on one small planet orbiting one unremarkable star, everything changed. Single-celled organisms became multicellular. Sponges appeared, then jellyfish, then worms. Fish evolved. Plants colonized the land. Insects took flight. Dinosaurs rose and ruled for 160 million years, then vanished in a mass extinction triggered by an asteroid impact 66 million years ago. Mammals diversified to fill the ecological niches left behind. Primates evolved. One lineage of primates descended from the trees, began walking upright, developed tools, discovered fire, invented language, built civilizations, and eventually constructed devices sensitive enough to catch the photons when they finally arrived. The timing is breathtaking in its improbability. This is not science fiction. This happened. The data is real, published in dozens of peer-reviewed papers, confirmed by independent observations from multiple instruments on multiple continents and in orbit. The photons were counted, their energies measured, their arrival times recorded to fractions of a second. The disturbance in the ionosphere was detected by monitoring stations in multiple countries. The afterglow was tracked across the electromagnetic spectrum for months. Every aspect of this event has been documented, analyzed, cross-checked, and made available for scrutiny by the global scientific community. What makes the deeper truth more than just physics is the context it provides for our existence. Gamma-ray bursts are not anomalies, they are not freaks of nature. They are a regular feature of the universe, as natural and as inevitable as the formation of stars and planets. The current best estimate is that somewhere in the observable universe, a gamma-ray burst occurs roughly once per day. Most are too distant and too faint to affect anything in our corner of the cosmos, but they are happening constantly. Stars are dying violently. Jets are being launched at nearly the speed of light. Beams of gamma radiation are lancing across billions of light years of space. This is what the universe does. It creates and it destroys in a continuous cycle of construction and demolition on scales that are almost impossible to comprehend. If you could somehow see the universe in gamma rays, as Fermi does, you would see a sky that flickers ceaselessly. Brief flashes, appearing without warning from random directions, shining for seconds or minutes, then vanishing. Each flash marks the death of a star. Each one signals the birth of a black hole. Each one represents the release of more energy than our sun will produce in 10 billion years of steady burning. The sky is not the peaceful, static, timeless dome that it appears to the naked eye on a clear night. It is a theatre of ongoing catastrophe, playing out on a stage so vast that most of its dramas are invisible to us. And among all those catastrophes, across all the decades of observation, GRB 221009A stands alone. Not because it was fundamentally different in kind from other gamma-ray bursts, not because it involved different physics or a different mechanism, but because of its singular combination of power, proximity, and alignment. Every few hundred years, a burst with this intrinsic energy probably occurs somewhere in the observable universe. But for one to occur this close to us, with its jet aimed so precisely in our direction, is something that happens perhaps once every 10,000 years. Our instruments have been watching the gamma-ray sky for roughly 5.5 decades. The probability of catching such an event in that narrow window was vanishingly small. Let that sink in. Consider what this implies about the events we have missed. In the 55 years since Vela first detected gamma rays from space, how many events of comparable or greater power have occurred outside our detection window? How many went off when their jets were not pointed at Earth? The jet of a gamma-ray burst covers only a tiny fraction of the sky, typically a few thousandths of the total sphere. For every burst we detect, perhaps 1,000 others occur with their jets aimed elsewhere. How many GRB 221009 A-class events have fired in the past century, in the past millennium, in the past million years, with their beams sweeping through empty space or illuminating galaxies we will never observe? The answer is sobering. The universe has been producing these events for billions of years. Our brief glimpse through a tiny window of technological capability has shown us one extraordinary event. The full picture, the complete census of ultra-luminous gamma-ray bursts in our cosmic neighborhood over the history of the universe, is something we will never fully reconstruct. We see shadows on the wall of a cave, and from those shadows, we try to infer the shape of the fire. There is a concept in astronomy called the observable universe. It is the sphere of space from which light has had time to reach us since the Big Bang, roughly 13.8 billion years ago. The observable universe has a radius of about 46.5 billion light-years, accounting for the expansion of space that has occurred during the light's journey. Within this sphere, there are an estimated 2 trillion galaxies, each containing anywhere from millions to trillions of stars. The total number of stars in the observable universe is estimated at something on the order of 200 sextillion, a number that, written out, would require 23 digits. Among those stars, some fraction are massive enough, rapidly rotating enough, and metal-poor enough to produce gamma-ray bursts when they die. That fraction is small. Perhaps one star in every 10 million or 100 million meets all the criteria. but applied to 200 sextillion stars over 13.8 billion years, even that tiny fraction produces a staggering number of bursts. The total number of gamma-ray bursts that have occurred within the observable universe since the first generation of stars formed, roughly 100 to 200 million years after the Big Bang, is estimated to be in the billions, perhaps tens of billions. Billions of events, each one a flash of energy that briefly outshines its entire host galaxy. Billions of jets, each one a beam of gamma radiation capable of sterilizing any planet unfortunate enough to lie in its path at a distance of a few thousand light years. Billions of black holes born from the corpses of the most massive stars. The universe has been doing this since the dawn of the stellar era, in an unbroken chain of creation and annihilation. Now consider our galaxy specifically. The Milky Way has a lower star formation rate than it did billions of years ago, and it has higher metallicity than many gamma-ray burst host galaxies, both of which reduce the expected rate of gamma-ray bursts. The current best estimate is that the Milky Way produces a gamma-ray burst roughly once per several 100,000 to a million years. Most of these bursts direct their jets away from the solar system. The probability that any given burst is aimed at Earth is perhaps 1 in a few hundred to a few thousand, depending on the jet opening angle. The rate of Milky Way gamma-ray bursts aimed at Earth is therefore estimated at roughly once per 100 million to a few hundred million years. On human timescales, this is rare beyond meaningful concern. The probability of a Milky Way gamma-ray burst threatening Earth in any given century is essentially zero. On geological timescales, however, the story is different. In the 4.5 billion years of Earth's history, with this rate, the planet may have been exposed to a significant gamma-ray burst a few times, perhaps more. The uncertainty in the rate is large enough that the number could be 0, or it could be 10, but the most likely estimate is a small handful. The deeper truth that GRB 221009A reveals is not about the specific burst. It is about the universe it exists in. It is about the fundamental character of a cosmos that builds complexity over eons, and simultaneously maintains the machinery to erase that complexity in seconds. There is no tension in this for the universe. The universe does not experience tension. It does not plan, intend, or care. The same nuclear physics that allows stars to shine for billions of years, providing the stable energy source that life requires, also dictates that the most massive stars will collapse in spectacular violence. The same gravitational physics that assembles planets from cosmic dust also compresses the cores of dead stars into objects so dense that nothing can escape their pull. Creation and destruction are not opposites. They are partners, linked by the same fundamental forces. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence. The atoms in our bodies were forged in stars. The calcium in our bones came from stellar nucleosynthesis. The iron in our blood was produced in supernova explosions. Some of those supernovae may have been accompanied by gamma-ray bursts that sterilized nearby worlds. The carbon in our DNA was made in the cores of red giant stars that lived and died billions of years ago. We are, in a very literal sense, the products of cosmic violence. We exist not despite the destructive tendencies of the universe, but because of them. And yet here we are, on a small blue planet, in a quiet corner of a spiral galaxy, in a cosmos that does not know we are here. We build telescopes to look outward. We build instruments to measure the energy of photons that have traveled for billions of years. We publish papers and hold conferences and debate the opening angles of relativistic jets. We try to understand. That effort, that striving to comprehend a universe that is under no obligation to be comprehensible, is perhaps the most remarkable thing about our species. Not our technology, not our cities, not our art or literature or politics, but the simple, persistent, almost stubborn desire to understand what we are and where we are and what is happening around us. There is another dimension to this deeper truth that goes beyond statistics and physics, and it concerns the nature of time itself and our relationship to it. Human beings experience time as a sequence of moments, one following the next, each lasting roughly the span of a heartbeat or a breath. Our plans extend a few years into the future. Our memories reach a few decades into the past. Our sense of history, at its most expansive, covers perhaps a few thousand years of recorded civilization. Beyond that, time becomes abstract, a concept we can name but cannot feel. The universe operates on a different register. The light from GRB 221009A traveled for 2.4 billion years. To say that duration out loud takes about 3 seconds. To truly understand, it requires a different kind of thinking, one that acknowledges the fundamental mismatch between human temporal experience and cosmic temporal reality. Consider this comparison. If the 2.4 billion years of that photon's journey were compressed into a single 24-hour day, starting at midnight, the entire history of complex animal life on Earth, everything from the first trilobites to the present day, would fit into the last 2 hours and 40 minutes before the following midnight. The age of the dinosaurs would occupy roughly 40 minutes in the late evening. The extinction that killed them would happen at about 11:22 at night. The entire existence of the human species, from our first emergence in Africa to this moment, would occupy the last 4 seconds of the day, and all of recorded human history, every empire, every war, every poem, every scientific discovery, would occur in the last 400ths of a second. 400ths of a second. That is our portion of the photon's journey. That is the span of time during which everything we have ever built, thought, written, discovered, loved, or mourned has taken place. And the photon, indifferent to all of it, was crossing the void between galaxy clusters, headed for a planet it did not know existed, carrying energy from a star that had already been dead for 2.4 billion years by the time it arrived. This temporal disparity is not just an intellectual curiosity. It has consequences for how we think about risk, about meaning, about the value of what we do. If a gamma-ray burst threatens Earth once every 100 million years, that is forever on a human scale. 100 million years is roughly 1,000 times the entire span of our species. No human institution, no civilization, no language, no memory will persist for even a millionth of that duration. The threat is real, but it belongs to a time frame that has no connection to human planning or experience. And yet, the burst that happened 2.4 billion years ago reached us today. The universe does not care about our timeframes. It operates on its own schedule, and that schedule can deliver a cosmic event at any moment, without warning, without consideration, without mercy. The once-in-100-million-year event can happen tomorrow as easily as in 100 million years. That is the nature of random processes. They have no memory, no schedule, no courtesy. There is a strange parallel between this cosmic indifference and the experience of standing on a beach watching waves. Each wave is the product of winds and currents, set in motion hundreds or thousands of miles away, hours or days before. The wave does not know you are there. It does not care that you are standing in its path. It is simply energy propagating through a medium, following the laws of fluid dynamics. A gamma-ray burst is the same, except the medium is space-time. The distances are billions of light years, the travel time is billions of years, and the energy is incomprehensibly greater. The principle, however, is identical. Energy, released at a distant source, traveling through a medium, arriving at a destination that had no say in the matter. We are standing on a beach. The waves are coming from very far away, and most of them miss us. But not all of them, and not forever. Now consider the broader picture of habitability. Life on Earth has been evolving for roughly 3.8 billion years. During that time, the planet has orbited the galaxy approximately 16 times. Since the Sun takes about 230 million years to complete one orbit around the galactic center. In each orbit, the solar system passes through different regions of the galaxy, regions with different densities of massive stars, different rates of supernovae, different environments of cosmic radiation. Some of these regions are relatively quiet and safe. Others are denser, more active, more dangerous. The spiral arms of the Milky Way, for example, are regions of enhanced star formation. When the solar system passes through a spiral arm, the density of nearby massive stars increases, and with it, the probability of a nearby supernova or gamma-ray burst. The time spent within a spiral arm is typically a few tens of millions of years, during which the local rate of cosmic violence increases. Between the arms, the environment is quieter. Some researchers have speculated that mass extinctions on Earth might correlate with passages through spiral arms. Though the evidence for this is debated and not conclusive, what is clear is that the solar system's journey through the galaxy exposes it to a varying level of cosmic risk over time. The risk is never zero, but it fluctuates. The current position of the solar system, between spiral arms in a relatively quiet region of the galactic disk, may represent a period of lower than average risk. We are, in a sense, between storms, crossing a calm stretch of galactic ocean before the next spiral arm arrives. That arrival is estimated to occur in roughly 30 to 50 million years, depending on the models used and the uncertainties in the galaxy's structure. This cyclical exposure to enhanced cosmic risk may have played a role in shaping the history of life on Earth. The periods of elevated risk might correspond to periods of elevated extinction. The periods of calm might provide the long, uninterrupted stretches of evolution that complexity requires. Life on Earth is not just shaped by chemistry and climate. It is shaped by the galaxy itself, by the rhythms of stellar birth and death that play out over hundreds of millions of years, too slow for any organism to perceive but powerful enough to determine which lineages survive and which do not. GRB 221009A came from outside our galaxy, from a distance so great that it posed no biological threat, but it served as a reminder that the same processes operate everywhere. In the host galaxy of the burst, 2.4 billion light-years away, any planet within a few thousand light-years of the dying star that produced the jet, and that happened to lie within the jet's narrow beam, would have experienced a catastrophic event. Its atmosphere would have been altered. Its ozone layer, if it had one, would have been damaged. Any life on its surface, if any existed, would have been imperiled. We will never know whether any such planet existed, or whether it harbored life. The host galaxy is too far away and too faint for us to resolve individual stars, let alone planets. But the physics tells us that the scenario is possible. Somewhere in that galaxy, in the aftermath of the brightest of all time, a world may have lost its sky. GRB 221009A, the brightest of all time, was a message written in gamma rays. It was not addressed to us. It was not addressed to anyone. But we received it. We decoded it. We spent years extracting meaning from it. And the meaning, when we found it, was both terrifying and beautiful. Terrifying because it reminded us of the scale of cosmic violence. Beautiful because the fact that we can be terrified by it, that we can perceive it, and think about it and feel something in response, is itself evidence of how extraordinary it is to be conscious in a universe this vast. Where does this leave us? What does the brightest of all time mean for humanity? Not as an abstract astrophysical event, but as a fact of our existence, a data point in the ledger of cosmic risks that ultimately governs whether technological civilizations persist or perish. The first and most obvious implication is humility. We are accustomed to thinking of ourselves as the central characters in a story that matters. Our economies, our politics, our personal dramas fill our waking hours and feel urgent and consequential. And in the context of human life, they are. But in the context of a universe that casually produces a flash of radiation visible across 2.4 billion light-years, a flash that could erase all life on a planet if it occurred nearby, the scale of our concerns shrinks to something almost infinitesimal. This is not nihilism, it is proportion. Understanding the true scale of the cosmos does not diminish the value of human experience. It contextualizes it. We are not less precious for being small. If anything, we are more precious because the conditions required for our existence are so specific, so contingent, so reliant on a sequence of events that could have gone differently at any point over 4.5 billion years. Every mass extinction that did not quite succeed, every asteroid that missed, every gamma ray burst that was aimed somewhere else. These are the margins by which we exist. They are thin margins, and knowing how thin they are should give us a kind of reverence for the improbable fact of being alive. The second implication concerns the Fermi paradox, the question first articulated by physicist Enrico Fermi during a lunch conversation in 1950. Where is everybody? If the Milky Way is roughly 13 billion years old, and if it contains billions of planets, many of which might be habitable, why have we found no evidence of other technological civilizations? The question sounds casual, but it conceals a profound puzzle. Even with modest assumptions about the probability of life arising and evolving to intelligence, the galaxy should have been colonized many times over by now. The absence of evidence for extraterrestrial intelligence is one of the deepest mysteries in science. Gamma-ray bursts provide one possible piece of the answer. In the early universe, when star formation rates were much higher and metallicities were much lower, gamma-ray bursts were far more frequent than they are today. The cosmic rate of gamma-ray bursts peaked roughly 10 to 12 billion years ago and has been declining since. In those early epochs, the rate of gamma-ray bursts within any given galaxy may have been high enough to periodically sterilize significant fractions of each galaxy, destroying any nascent life or resetting the biological clock every few 100 million years. If this is true, the window of cosmic history in which complex life can evolve and survive long enough to develop intelligence may be narrower than we assumed. Not the first few billion years, when gamma-ray bursts were too frequent and too devastating. Not the far future, when star formation has declined and fewer suitable planets exist. But a window roughly centered on the present epoch, extending perhaps a few billion years in each direction. We may be living in the cosmic spring, the season when the frequency of gamma-ray bursts has declined enough to permit the long, uninterrupted stretches of biological evolution that complexity requires, but before star formation winds down to the point where new habitable worlds stop being created. Some researchers have extended this idea further. They point out that the habitability of a galaxy depends on location as well as time. The inner regions of galaxies, where star formation is most active and massive stars are most concentrated, may have higher gamma-ray burst rates than the outer regions. The galactic habitable zone, the region of a galaxy where conditions are most favorable for life, may therefore be an annular ring in the outer disk, far enough from the center to avoid the highest burst rates, but close enough to benefit from sufficient metallicity for rocky planet formation. Our solar system, located roughly 26,000 light-years from the center of the Milky Way, about 2/3 of the way out in the galactic disk, sits comfortably in this zone. Whether this is coincidence or a selection effect, a consequence of the fact that life can only observe itself in regions where it survives, is an open and fascinating question. There is a third implication, more personal and more philosophical. It concerns the meaning of safety. Human civilization is, in one reading, a vast apparatus for managing risk. We build shelters against weather, we construct levees against floods, we develop vaccines against disease, we create institutions to mediate conflict. We send spacecraft to catalogue asteroids that might strike us. Risk management is embedded in every aspect of our social and technological fabric. But there are risks that no apparatus can manage. A gamma-ray burst from a collapsing star within a few thousand light-years of Earth would arrive at the speed of light. The gamma rays and the first visible light from the event would reach the atmosphere at the same moment, giving literally zero warning. There would be no alert, no siren, no evacuation plan. The first sign would be an immediate and severe disturbance in the ionosphere, followed over weeks and months by the depletion of the ozone layer and the cascade of ecological consequences that would follow. Elevated ultraviolet radiation, damage to photosynthetic organisms, disruption of food chains, and potentially a mass extinction comparable to the worst in Earth's history. There is no technology we possess or can currently conceive that would protect against this. You cannot intercept a beam of photons. You cannot deflect gamma rays. You cannot build a shield large enough to cover a planet. The only protection is distance and luck, the same protection that has served Earth for 4.5 billion years. It has worked so far. The odds are overwhelmingly in its favor for any given century or millennium. But forever is a long time, and the universe is patient in a way that organisms are not. This is a discomforting thought, but it need not be a despairing one. The probability of a destructive gamma-ray burst in any given human lifetime is immeasurably small, far smaller than the probability of many other risks that we face and routinely ignore. It is smaller than the risk of a large asteroid impact in a given century. It is smaller than the risk of a supervolcanic eruption. It is incomparably smaller than the risks we pose to ourselves through nuclear weapons, climate change, or engineered pathogens. Gamma-ray bursts belong to the category of existential risks that are understood, acknowledged, and filed under the heading of cosmic contingency. They inform our philosophy more than our policy, but they do inform our philosophy. They change the way we see the night sky. On a clear night, far from city lights, you can see roughly 2,500 stars with the naked eye. They appear serene. They appear eternal. They are neither. Every one of them is a nuclear furnace, consuming millions of tons of hydrogen per second, held in a precarious balance between the inward pull of gravity and the outward push of radiation pressure. Some of them will exhaust their fuel and collapse to white dwarfs, slowly cooling over trillions of years. Some will explode as supernovae, scattering their constituent elements into the interstellar medium, seeding future generations of stars and planets with the heavy elements necessary for life. And a tiny fraction of them, the most massive and rapidly rotating, will produce gamma-ray bursts. When they do, a beam of radiation will lance outward at the speed of light, carrying more energy than our sun will produce in its entire existence. That beam will travel for millions or billions of years, crossing the spaces between stars and galaxies, until it either strikes something or dissipates into the ever-expanding emptiness. If it strikes a planet with an atmosphere, it will strip away the protective ozone layer. If it strikes a planet close enough, sterilize the surface entirely. If it strikes nothing, it will simply travel on, carrying its message of cosmic violence deeper and deeper into the void, until the expansion of the universe redshifts it into oblivion. You are looking at the universe when you look at those stars. Not a painting, not a simulation, not an image on a screen. The actual universe in real time, pouring its light across the void and into your eyes. Some of that light started its journey before you were born. Some of it started before your civilization existed. And somewhere out there, right now, as you listen to these words, a star is collapsing, a jet is forming, and a beam of gamma radiation is erupting outward into the darkness. It is almost certainly not pointed at us. Almost certainly. There is a kind of peace in that almost. Not false peace. Not the peace of ignorance. The peace of understanding. We know what is out there. We have measured it, modelled it, published papers about it. We know the odds, we know the physics, we know the history. And armed with that knowledge, we continue. We go to work. We raise children. We plant gardens. We build telescopes to look deeper and further, knowing that what we find will not always be comforting. Knowing that the universe offers no guarantees and choosing to look anyway. And this brings us to a final reflection that is difficult to articulate but important to acknowledge. The detection of GRB 221009A was not just a scientific event. It was, in a quiet and understated way, a cultural event. It forced a conversation about cosmic risk that usually remains confined to academic journals and specialist conferences. News outlets around the world reported on the boat. Science writers and communicators explained gamma-ray bursts to audiences who had never heard of them. For a brief moment, the general public was invited to consider something that astronomers think about routinely, but that most people never encounter. The fact that the universe can produce events of overwhelming power, that these events are a natural and ongoing part of cosmic activity, and that the safety of our planet from such events is not a certainty but a probability. That conversation is valuable, not because it should cause fear. Fear is not the appropriate response to a risk this remote, but because awareness of our cosmic context is a kind of maturity, a species that understands its position in the universe, that knows the scale of the forces operating around it, that can measure those forces with precision and assess the associated risks with honesty, is a species that has earned something. It has earned the right to call itself aware. And awareness, however uncomfortable, is always better than ignorance. We live in a universe that does not owe us an explanation. It does not owe us safety. It does not owe us meaning. Whatever explanation, safety, or meaning we find by our own effort, through observation and calculation, and the painstaking work of building a picture of reality that is as close to the truth as our instruments and our minds can achieve. That choice, the choice to keep looking, to keep asking, to keep understanding even when the answers are frightening, is the most human thing there is. It is what separates us from every other arrangement of matter in the known universe. The stars do not wonder about themselves. The galaxies do not ask why they exist. The black holes do not contemplate their own nature. Only we do. Only we stand on our small blue world, tilt our heads back, and ask, what is that light? And when the light turns out to be the dying scream of a star 2.4 billion light-years away, a scream so loud it shook the ionosphere of our planet, we do not look away. We lean closer. We listen harder. We try to understand. On a single day in the autumn of 2022, the universe spoke, not in words, not in any language that human ears could hear or human tongues could replicate. It spoke in photons, in gamma rays, a pulse of energy that had been travelling since long before any eye had opened on Earth, and that arrived just in time for a species that had, only decades earlier, learned how to listen. The message was not directed at us. There was no sender and no intent. The universe does not address its correspondence. But there was a message nonetheless, encoded in the energy spectrum and the light curve and the arrival times of photons that had crossed 2.4 billion light-years of expanding space. And if we choose to hear it, it speaks to us about ourselves as much as about the cosmos. The message is this: you are here because nothing has gone catastrophically wrong yet. You exist because no gamma-ray burst has been aimed at your planet during the critical epochs of your evolution. You have bones made of calcium that was forged in dying stars, blood carrying iron that was once part of a supernova, a brain built from carbon assembled by red giants that burned out before the Earth existed. Your body is a library of cosmic history, every atom carrying a provenance that stretches back billions of years, and the unbroken chain of biological continuity that connects you to the first self-replicating molecules in Earth's primordial ocean has persisted for roughly 3.8 billion years without being severed by any cosmic catastrophe. Not one of your ancestors was on a world that lost its ozone layer to a flash of gamma radiation from a collapsing star. Not one of them experienced the darkened skies and elevated ultraviolet that would follow such an event. Not one of them was caught in the wrong place at the wrong time in a galaxy, where the wrong place and the wrong time are defined by the random orientation of jets from dying stars thousands of light-years away. That chain of survival is what produced you. It is long and fragile and depends on conditions that are neither permanent nor guaranteed. GRB 221009A was a reminder of this fragility. It was also, and this is less often noted, a celebration of resilience. Not the resilience of any individual or nation, but the resilience of life itself. Life on Earth has survived 5 major mass extinctions and numerous smaller ones. It has persisted through asteroid impacts, supervolcanic eruptions, ice ages, and episodes of extreme global warming. It has endured whatever gamma-ray bursts may have swept through the neighborhood during the past 4.5 billion years. Life is stubborn, it finds ways. It crawls into crevices, dives into deep oceans, hides underground, goes dormant, adapts, evolves, and comes back. The individual is fragile, the lineage is astonishingly tough. There is a deep comfort in this toughness, even if it is not the kind of comfort that protects any particular generation. The species may be at risk from cosmic events on geological timescales, but life itself in some form has a remarkable track record of survival, and the fact that one branch of that life developed the ability to detect and understand events like GRB 221009A is itself a triumph of evolution, a demonstration that complexity can arise and persist even in a dangerous universe, given enough time and enough luck. The boat was the brightest gamma-ray burst in the history of human observation. It may hold that record for centuries, it may hold it for millennia, or it may be surpassed next year by something even more extraordinary. We do not know. The universe follows no schedule and offers no previews. What we know is that it happened, that we saw it, that we understood it well enough to be humbled by it, and that the understanding itself is an achievement worth noting. Because here is the final truth that the brightest of all time teaches us. It is not about the burst. It is about the fact that we know about it. 2.4 billion years ago, a massive star in a distant galaxy ran out of fuel, collapsed under its own gravity, formed a black hole, launched 2 jets of relativistic matter, and died. That star did not know what it was doing. It could not know. It was matter and energy following the laws of physics, nothing more and nothing less. The jets erupted, carried energy across the cosmos, and photons began their long, lonely journey through expanding space. During that journey, on a planet that the dying star would never know existed, in a galaxy the dying star had never interacted with, a species evolved that built instruments capable of detecting those photons when they arrived. That species counted the photons, measured their energies, calculated the distance, reconstructed the history, published the results, debated the meaning, felt awe and fear and wonder and a deep aching sense of smallness that is itself a kind of grandeur. The star did not know, but we know, and knowing is the thing that matters. Not because knowing changes the physics, not because knowing prevents the next burst, not because knowing makes us safe. Knowing matters because it is the only light we can shine back at a universe that is, in every other respect, dark and indifferent. We cannot match the energy of a gamma-ray burst. We cannot outlast the stars. We cannot see beyond the edge of the observable universe, but we can understand what we see. We can measure it, model it, record it, and pass the knowledge on. That is our jet. That is our beam of energy, focused not across billions of light years of space, but across generations of human time. From mind to mind, from century to century, from the first astronomer who looked up and wondered to the scientists who will, centuries from now, still be extracting information from the data gathered on October 9th, 2022. The stars will continue to die, the jets will continue to fire, the beams of gamma radiation will continue to cross the cosmos, illuminating nothing that can see them, striking nothing that can feel them, except, very rarely, the instruments of a species that learned to pay attention. On the night of October 9th, 2022, the sky looked perfectly ordinary to anyone standing outside. No flash of light was visible, no sound was audible. The sun had set or was setting depending on your longitude. The stars came out as they always do. People went about their lives. They ate dinner, watched television, put children to bed, walked dogs, argued about politics, worried about bills. The world felt normal because it was normal. At the scale of human experience, nothing had changed. But quietly, invisibly, at the speed of light, a pulse of energy from 2.4 billion years in the past arrived at Earth. It passed through the atmosphere in a fraction of a second, deposited some of its energy in the ionosphere, triggered alarms on satellites, and told us something about the universe that we will spend decades fully absorbing. It told us that the cosmos is beautiful. It told us that the cosmos is violent. It told us that beauty and violence are not opposites in the language of physics, but aspects of the same underlying reality. And it told us, in the only language the universe speaks, the language of energy and matter and time, that we are here, that we noticed, that for now, for this brief moment in the nearly 14 billion year history of everything, we are still safe enough to wonder about it all. The stars do not care, the galaxies do not care. The black holes and the relativistic jets and the gamma-ray photons speeding through the void do not care. Nothing out there cares. The universe is not cruel. It is not kind. It is not anything that requires a human adjective. It simply is. But we care. We look up and we wonder and we measure and we try to understand. And when the universe produces the brightest of all time, a flash of energy so powerful it shakes the ionosphere of our planet from 2.4 billion light-years away, we do not turn away. We do not hide. We build better telescopes. We write better models. We ask better questions. And we pass on what we learn, so that those who come after us will know a little more about the cosmos they inhabit, and the thin, precious, improbable thread of luck that allows them to be here to wonder about it. That is the legacy of GRB 221009A, not the energy it released, not the records it broke, not the papers it inspired. Its legacy is the reminder that we are awake, that we are paying attention, and that in a universe vast beyond comprehension and violent beyond imagination, the most extraordinary thing is not the gamma-ray burst. The most extraordinary thing is that the small blue planet noticed.